So I'm going to show you how to analyze the data you collected using a textural analyzer for the rheology of the solids lab. Basically in the lab what you got is a FD curve. So where F is the force in Newton you are applying, D is the deformation in millimeter you are collecting. So basically what you had is you had I believe a potato cylindrical object. I believe the height is 20 millimeters and the diameter is 20 millimeters. So the area is pi by 4 into 20 millimeter square, right? And you applied the force. As you applied the force, the material start deforming and the computer basically recorded it. So basically your graph might have looked like this. That's the maximum point you loaded it. And then when you start unloading it, it basically comes and it ends basically over here. And if you remember, this is going to be the elastic strain or the elastic deformation that got rebounded, and this is the plastic deformation, right? And also one of the problem asked was to determine the area under the curve. And for that what we are going to do is we are going to consider only the loading curve like this, okay? And we have to calculate the area under the curve. How can I do the area under the curve? What we are going to use it called as a trapezoidal rule. In a trapezoidal rule, basically you are going to split the curve into multiple segments. And if you take this multiple segment, if you want to determine the area under this trapezoid, what you are going to do is if this is y1, if this is y2, or maybe I should call it as the f1 and the f2. F1 and f2. Let's call it as this is f1, this is f2. Let's call this as this is d1 and this is d2. The area of the trapezoid is equal to the delta d times the average of the two heights, which is f1 plus f2 by 2. So delta d is d2 minus d1 into f1 plus f2 by 2. So that will give you this area under this one line segment. If you keep calculating all the line segment, if you sum it up, you get the area under the curve. And if this is in Newton, if this is in meter, the Newton meter is the joules. That is the energy required for a compression of a potato cylinder. How much work is performed to compress that cylinder. That's what it's about. So what we do is let's go back to an Excel sheet. Let's take an example data set and let's try to do the calculation. Okay. So I'm going to switch to an Excel sheet where basically what I have plotted is, pay attention, I have the distance as the first column and force as the second column, and you need to plot them. So I basically plot the two curves and this is how it looks like. The force is on the y-axis and the deformation is on the x-axis. This is the loading curve and it loaded up, and then during the unloading it came and then it stopped here. So basically if you look at here, let me go to the pen and then draw it. So this is the elastic strain. This is the plastic part which didn't get deformed. And then now we need to determine the area under the loading curve. So let's go back. How can we do that? I have the force and the distance, and I have to calculate the area. The area is going to be Newton millimeter, right? And that can be calculated as I'm going to zoom in a little bit so that you can see how I type the formula. Okay. That is going to be, I'm going to ignore the first row. The second row is going to be average force or the average height times the difference between the two distances. So that is the area for the first point. And then what you need to do is you need to calculate it for the entire length. Okay. And you can see that initially the value was pretty close to 0. We collected at a very high sampling rate. Probably that is not needed. So you keep going until you see the maximum force. The maximum force occurred at around 8.11. So basically, if I sum all the values until that point, I will basically get the area under the loading curve, and that will give me in Newton millimeters. Because it's really 0, I could stop it theoretically, but let's go anyway there. So basically for this problem, the energy required to compress the cylinder is about 4 Newton millimeters. So if I want it in a good units, then it's going to be divided by 1000, and that will give me Newton meter, and that is nothing but joules. So that's how you would calculate area under the curve. Present